Like you would be surprised how many features you don't know about Zoom. We use it every day, and like every day I see new things. Like this practice and life thing is like I've never seen it before.
Oh yeah. No, there's new stuff to it. I haven't noticed. Charlotte was showing me some new stuff you can do with it.
Hey, Yorgi, you're always the first.
Hello, everybody. We'll get started in a couple minutes. We'll let other people join in. But thanks for tuning in. How are
Don't,
you
don't, don't get me wrong, Yorgi. You're always welcome. It's just like, as soon as we go live, you're there.
guys?
We should invite him here, by the way. So I think this is great to have him here. I think he's trying to practice. So
He is always on time. We have a loyal fan.
nice. How things
Oh,
on your side, Mike?
What's that?
How things on your side?
Good, good.
I'm looking forward for this session. We give it a couple of minutes for people to join. So if you're watching us live now, feel free to leave your questions. And if you're watching us in recorded mode, make sure to post your questions on the community Slack.
yeah. How's the weather over where you are, Fawaz?
It's sunny but windy. So yeah, I'm currently in Liverpool, northwest in the UK. So we had like a couple of days which were really windy, and if you like me, you run outside, it's like, if it is like, in your face, you feel like you're not moving at all. So
Yeah.
I'm looking forward like for really calm weather here. How's the weather over there?
It is good here. Can't complain. I love a good sunny day. It's a little overcast today, but not too bad. All right. Well, looks like we got a few more people. Let me get started. All righty. Well, good day wherever you are joining us from today. I'm Melissa Riley, your co-host, joined by Dr. Fawaz Ghali and our new guest from Hazelcast, Senior Solution Architect, Mike Yawn. Welcome, and how's it going, guys?
Really good.
Awesome.
Yeah, it's great. Yeah, thanks for running these sessions, Mel. It's great to have everyone here. So we welcome everyone. We're trying to get most interesting topics. So if you're watching us live now and you would like to know more about specific topics or features in Hazelcast, let us know. We would be happy to actually have specific or advanced topics in using Hazelcast, whether it's a deployment or development or specific features. So we welcome your feedback as well.
Yes. Well, we are thrilled to explore gRPC and its integration with Hazelcast Platform today. Before we dive into the content, a quick heads up, this session is being recorded and you'll have access to the recording for later viewing. Also, feel free to fire away any questions you have in the chat, and Fawaz or Mike will address them either on the spot or during our Q&A session. Well, now, without further ado, over to you, Fawaz.
Thanks very much, Mel. So welcome everyone, and it's very exciting to have you all here today. We try to stick to a schedule on monthly basis for running the Hazelcast office hours, and I'm very excited today to have Mike Yon to talk about the gRPC based microservices. So welcome, Mike. How's it going?
Going real well, thanks.
So perhaps before we dive into the topic, could you just describe a little bit about the Hazelcast platform and how is that connected to gRPC and the overall for this session today?
Yeah, so gRPC is kind of a general purpose remote procedure call mechanism. And Hazelcast, of course, we have, besides our fast data store, we have various ways of doing distributed compute. And so there is a built-in, and we'll talk about some of this as we get into the presentation. There is a built-in connection between Hazelcast and gRPC in kind of the outbound direction, that if I'm writing a pipeline, I can invoke code that's been implemented as a gRPC service that may be running locally or might be on a remote system somewhere. And so that's a real, well-established, well-defined integration. But, just because I have to be different, I wanted to go the other direction. I said, well, what if I actually want to implement a gRPC service using Hazelcast and have that called from outside? And that's not a built-in integration. And so that's kind of the project I built. And when we look at it, we'll kind of see why it's not built in. There is kind of a mismatch that kind of, you kind of have to pound a square peg into a round hole to make this work. But I still found it an interesting exercise. It kind of, was fun to work on, and it might be useful to someone. So I kind of wanted to share. It just gives you another way of thinking about doing distributed compute on Hazelcast.
Yeah, so this is great to hear. So gRPC is one of the many tooling we have at Hazelcast. We have so many tools, APIs, clients, and connectors. So what we're looking today is just to figure out how gRPC fit into this picture and how you can also use it as a source and sync. So I'll hand it over to you, Mike. For anyone watching us live now, feel free to leave your questions. We will take these questions from LinkedIn, Twitter, YouTube, and I will make sure to ask Mike. And if you're watching it in recorded mode, make sure to actually sign up for the community Slack where you can get access to the Hazelcast features, which we will talk about today. So over to you, Mike.
All right, thanks, Fawaz. Yeah, as I said up front, this is kind of a project that I've been working on. I actually set out to do implementation of microservices in Hazelcast, and just along the way of kind of building a demo of that, decided to use gRPC as the communication mechanism. So why that looked like a good fit for me. Spring Boot is actually probably the most common way that people build microservices on Hazelcast. And I had nothing against that. There were just already a lot of demos built for that. So I didn't want to create yet another demo that looked like the others. So this was a chance to do something a little bit different. gRPC is an open source RPC framework. It comes from Google, who obviously knows something about scalability. It supports a lot of different languages, including all of those where we create Hazelcast clients. It is based on the protocol buffers technology, which is one of the serialization formats we support. So kind of if you did a Venn diagram of the things that Hazelcast supports and the things gRPC supports, there was a good overlap there. And gRPC is widely used for microservices, so it felt like a good fit. Now, flipping that around from the other direction, if you're using gRPC, why would you want to use distributed compute in Hazelcast, and specifically the Jet stream processing piece, rather than some other implementation technology? And I'll say right up front, if what you're doing is really a very simple task, you probably don't need to, because where we kind of excel is if you have a complex workflow that involves multiple stages, where you can benefit if you can get some concurrency going between those stages. So the samples that I built are not good samples of things that you would do, with gRPC and Jet together, because they're very trivial. But once you have a more complex workload, like calling out to a machine learning inference algorithm to do fraud detection or something like that, then you can really benefit from the concurrency that we can provide. Other benefits, and these are really just the standard benefits when we talk about our platform. We have fault tolerance so that we can recover from a node failure. We can scale up and down while jobs are running. That's actually an enterprise level feature. But we can do recovery of jobs from an outage. Depending on whether you're using sources and sinks that support this, but we can support at least once or exactly once execution where you need that. We have our own threading model, as I said, that gets us a really high degree of concurrency. We can have low latency because we can use our fast data store for both state of the processing that's going on, but also for reference data that we might be needing to look up or enrich data coming in. It is largely self-balancing. You don't have to worry about, how big a thread pool do I need to create for each task. The way the back pressure and queues work, it just kind of balance itself very well and adapt to the workload if that changes. And we have lots of connectors to sources and sinks, including gRPC, to let you hook together into whatever the data sources that you're using. So I kind of wanted to go out, people may already be familiar with gRPC, but if you're not, I wanted to do a quick overview. So this part is not Hazelcast specific at all. Essentially, it started out with protocol buffers, which was a way of defining messages, and added to that an extension to define APIs that says, here's what the request message is going to be, and here's what the response message is going to be. And then those messages can either be simple, unary, meaning there's just a single parameter, or they can be streaming, which means there's not just multiple parameters, but actually a varying number of parameters. So, given the fact that both the requests and the responses could be either unary or streaming, that gives us 4 different method signatures we could potentially support. And we'll go into that right here. So for my testing, I created one method for each of these 4 possible signature types and a trivial API for each. So for a unary message, it's just a hello. You pass your name in as a message and it comes back and says hello with your name. For client streaming, I did a simple calculator. I send over a stream of numbers, and once I say that's the stream of numbers, it just sends me back the sum. So a stream of numbers going the client direction, a single response coming back. To flip that around, in order to send a single request and get multiple responses, that's like a typical subscribe type thing. So I can say subscribe to this topic, and then I will receive a stream of messages back that were published to that topic. And then bidirectional streaming, I actually don't like this one. I'm going to replace it at some point, but it's just a chat server. So, if I have a chat going, I don't necessarily have to wait for somebody to respond to everything I send. I can send a message. I can send another message to that user. I can send a message to a different user. So I can, have multiple bidirectional streaming chats open with different users. So that's kind of the set of unit tests I built for this. Now, if we look at, the way you define a gRPC service is with a .proto file. And so this is the header part or the top part of my .proto file. I called my service examples, and I said, here are my 4 APIs that I'm going to implement. They all say RPC, the name of the service, the type of request message. 2 of them are simple, unary, 2 of them are streaming, and then the type of the response message. So pretty straightforward. I just split this up so that it's easier to read to fit on the slides. The second part of the file is my message definitions, and it's just, what is the message type? What are the fields and the types within that? So that's the services that I am going to play with. So again, talking standard gRPC here, we then take our proto file and we run it through a protobuf compiler, which gRPC provides. And that gives us a couple of different output files. The first thing is all of the messages. And then the second one is the actual gRPC kind of a stub implementation. So those two files come out, and then we can build our application based on those. Another piece that they give us to start with is the gRPC server. So this is what's going to run on the host or the service side. And I didn't have to write this code. I just cut and pasted it right off of the gRPC website. I did add one line because of problems on my side. I found that early in my testing, didn't mean to advance that. It's not letting me highlight. I had a bug in my pipeline at one point. And so the pipeline actually kind of fell over and died, but the request kept coming in. And gRPC dynamically just created threads for each new request coming in. It will reuse threads when it can, but since I hadn't responded to any of the incoming messages, it couldn't free up those threads. So in order to throttle this, I added the line about creating a fixed thread pool. So we won't try to create more than 16 threads for inbound messages with this. Now that my code is completely error-free, I could take that back out, but it's probably a good backstop to have there, that if for some reason the pipeline's not running, we won't just keep creating an endless number of threads. So first I implemented this. I wanted to show, we're still doing this without Hazelcast in the mix. How would I implement the server side of this? And so the way I do that, first of all, the protobuf compiler created a base class for me, which, since my service was called examples, it created examples impl base. So I need to extend that. I need to start up that gRPC server that we just saw. And then I override the methods within the impl base to put in my actual implementation of each one. So I'm not showing all four of them here, just the simple hello message. I say I've got a request coming in, and then I have a potential stream of responses going back. Now, I know that this is a unary call, that there's only going to be a single response. But to make the API consistent, the API always looks like this, whether it's simple or streaming. So I just build my response. This response builder is, again, something that gRPC generated for me based on my proto file. I set the actual response field using the request that came in, build that, and then on the response observer, I say, here's my response. And since it's a single response, not a streaming response, I say, and that's it. I'm complete. I'm done. Send that on to the client. So that's all I have to do to implement the server side. So as far as the client side, how would we consume this service? We specify the target that we want to connect to, which is where that gRPC server is running. And then I use the gRPC managed channel builder to say I want to open a channel up to that target, and then say build. And once the channel is open, I can get stubs from that channel that allow me to communicate with the server. Now, there's 3 different kinds of stubs here, depending on what sort of interaction you want to do. We will go through all 3 of them. But realistically, you would probably pick one and stick with it. So it's only because I wanted to test all the different combinations and permutations to make sure everything worked. Am I creating all 3 of these stubs? Like I say, you probably, depending on what your application requirements are, you would pick one and stick with it. So here are the 3 ways I would call these different stubs. I'm actually going to start with the one in the middle because that's the simplest one. Is a blocking call. That's what we're probably most used to dealing with in either local or remote procedure calls, which is I just make a call, I pass in my request, it's going to block until the response is ready, and then my response will come back. So that's really the simple way to do it. I also can have a async one. That's the one at the top, where again, I still pass a simple request, but then I actually pass it an observer that says, this is essentially a callback you can use whenever you have a response ready. You can call the on next message that'll notify me, and that response observer then handles the response when it comes through. And then finally, I can do a future stub where I just send a request. I get back a response immediately, but that response is a future that I can then at some point call get on the future to actually see the response. And if you're used to working with futures, you can do all the things you're used to doing with futures. There's various ways to say, hey, I want to, grab the first one that comes back, or I want to wait till, if I have multiple things that I've sent, I can wait and collect all the responses together and say, I don't want to continue until I get all the responses. We haven't looked at integration with our Hazelcast pipelines yet, but the pipelines have a nice integration with this so that we can wait for the future to come back. So we did see there were like 4 different types of API signatures we could have done. There were also 3 different stub types we could do. You can't mix and match these completely frequently or freely. There are some limitations. So I just created this little chart to say, what are the legal combinations? If you're doing a unary call, you can actually use any of those stubs, as we saw with the say hello. But if we're doing, for example, bidirectional streaming, you can only use the async stub for that. It's the only one that can handle streaming in both directions. So, Fawaz, interrupt me because I've got this in full screen mode, so I'm not seeing the chat. If there's any chat questions at any point, feel free
Yeah,
to.
yeah. So maybe like if you go one slide back, please. And
Yeah.
from experience, what would you say? This is a question coming in the chat. What would you say most common uses for each of these subtypes?
I tend to use futures more. I am not experienced enough with gRPC to know everywhere, but if as an application developer, if there's nothing else I can do, if it's like, hey, I am, you know, saying doing a credit check, that's one of my, it's like, I can't process this transaction until the credit check, finishes. So I might as well block because there's nothing productive I can be doing in the meantime. But as soon as you start trying to say, but I'm going to have multiple requests in flight at the same time, that's when you start looking at these other models and saying which stub is going to best fit the programming style that I'm trying to use. So it's largely going to be determined by application requirements, and you know I tend to use more of the future and async types than the more trivial blocking one. But the blocking one is definitely easier to get started with. It's probably what we're most familiar with. Do
Yeah.
you have anything to add there that
Yeah, I agree here. It depends on the use case. So it will be nice to hear what is the use case for this question. So anyone is watching us now, let us know if you actually use the gRPC with Hazelcast. I know from experience that if you are in data science, machine learning, you're probably gonna end up using async with bidirectional streaming. So we're gonna cover a little bit on map using Python and map using as a service. So this will be in this session later on. But again, it depends on the use case. So I've been using bidirectional async mainly for connecting machine learning models and deploying using Jet. So this is one use case if you plan to use gRPC with Hazelcast.
So now I want to look at the integration that's already built into Hazelcast to work with gRPC. And this I copied directly out of our reference manual. Within gRPC, you can define a gRPC service when we're defining one here that takes as a request message. Remember when we defined our protos, we had a request type and a response type. So the request type is going to be a product info request. The response type is a product info reply. And we essentially define using the service factory type that there's a gRPC service out there somewhere that knows how to respond to this product info request and give us a product info reply back. So we define this as a unary service. We can also, only two of the four types are built into Jet, unary service and bidirectional streaming service. Now, I haven't tried it myself, but I imagine you can do the client streaming or server streaming by defining it as a bidirectional streaming service and just send the complete after you send a single item. So I think we probably map to all four of those. You remember that we, on our client side, needed to use the managed channel builder. So here we say managed channel builder for whatever our host and port is, which are defined, elsewhere in the file I didn't copy. And then essentially say we want to use the gRPC product service and get a stub that allows us to talk specifically to the product info API there. So we do that service factory definition somewhere before we start building our pipeline. And then excuse me, I need to sit here. Within the pipeline, we have a stream of trades that we're processing. And in one of our pipeline steps, we can call map using service. We want to call the async variation of that so that we don't block our pipeline. We reference the product service, which is what we declared up there with the service factory. And we pass the service reference and then the trade, which is the item that's passing through the pipeline. And then for each one of the trades that come through, we build a request using the product ID off of the trade, and then we return or we call the service. And then when that service returns to us, we map that reply into a tuple that gets passed on to the subsequent pipeline stages. So I'm kind of going through that really briefly. I think there's a better description of that, kind of in the full documentation. But if you've used the, map using service, this is familiar. If you've never used it before, then that's a lot of stuff to kind of say, what's exactly going on there? But this is how jet pipelines call out to remote services generally. And then the gRPC service is a specific implementation of that, where we know that this product service has been implemented somewhere as a gRPC service, and we can implement it. I'm actually going to stop there and hand over to you, Fawaz, because I know you did a blog post recently talking specifically about the various flavors of map use, not just map using service, but like map using IMAP. There's a lot of different API calls within the distributed compute capabilities of Hazelcast to let us call out to these service APIs. I find them to be very useful in lots of cases, and I think you can talk about either generally or specifically for invoking machine learning. Do you have something you want to share that I should stop sharing, or you want to just talk off the cuff about that?
Yeah, so no, I don't need to share. So we are actually posting the link for the blog post that you mentioned now for anyone interested to know more about map using service, which Mike mentioned here. Essentially, what we want to cover for this part here is creating data pipelines. So this is the ultimate goal for using map using service. We want to transform the data from raw data into some type of features, which is like if you're interested or you're using machine learning, you probably have dealt with features to train your models or to serve your models. So Hazelcast, with creating data pipeline, you can use map using service to do this transformation. You move raw data into actually features. And there are two ways to do it. We have batch processing or stream processing, which what we're trying to focus on for the gRPC. Obviously, we have also between batch and streaming, we have either stateless or stateful scenarios. But again, if we look at map using, essentially it's based on Java Lambda function, which what you see it here on the screen. Mike is sharing. So the Java Lambda, if you're familiar with Java Lambda, essentially it allows you to write multiple comments, expressions. So you define your argument and your body for your function. And this can have different implementation. So one could be map using IMAP. So if you want to define your IMAP, you can basically create a stream stage. And from the stream stage, you can connect it to a Kafka source. You specify your Kafka topic, and from there you can do some data transformation. So you can get order details or count how many orders you receive per window. So this is map using IMAP. The other one, which is more familiar, is map using replicated map. So this is a different approach from IMAP, but the one which is quite popular and actually is being used by our data engineers is map using service. So map using service, so we have map using Python, which allows you to run and deploy your machine learning models. So the idea of using gRPC with map using Python is to actually specify which model you want to run. So this will have the same effect as creating a stream stage. And from there, you can define using the gRPC, which we discussed the async type of it in bidirectional streaming. And the gRPC call will allow you to run your Python model. So .py, that's where you store your machine learning model, and you can invoke it from Jet. And this is open new doors because it allows you to run the same model in distributed compute using Jet, which is something if you wanted to run it in different tools, you probably need to build your IT stack or ML stack. Whereas in Hazelcast, what you can do is define your Jet job, and within Jet job, you define your stream stage, your source, and as a stage, you can define Python transform, which allows you to use map using Python to run your machine learning model. So this is really useful because it allows data scientists to work on the models, create the features, and train the models, and the ML ops to focus on deployment for machine learning models. And this will needs, obviously, if you're creating features, you can use Hazelcast Jet stream processing to ingest raw data and convert it to features. So there is a blog post. We will make sure to post it in the chat box. So feel free to have a look at map using service. And if you have any questions, let us know in the chat box, or if you're watching in recorded mode, make sure to leave your questions on the community Slack. So over to you, Mike.
All right, thanks. So now we get into the project, as it will, where I wanted to kind of like see how we could implement the service itself as a Hazelcast Jet pipeline. So that was my idea, is that I wanted a gRPC source. Now, there's a bunch of built-in sources and sinks in Hazelcast, but there's also a nice extensible API where you can build your own. So it's like, well, I want to build my own gRPC source that I can use to read from in a pipeline, and a gRPC sink that I can write to. And that's really all I need to be able to interoperate and implement those gRPC services. The obstacle is that Jet really is designed to be point to point. It's like I'm going to read from a sink, maybe Kafka, going to do all my transformations. I'm going to write to something else. Maybe it's a database or something else, but it's not really built around the idea of a round trip, that the response is going back to the same place as the origin. So that was kind of one of the things that I had to account for is that sources and sinks are really independent. And for this to work, I had to link them together. I had to say, well, I need to make sure that that response message goes back to the same client that sent the request in. So if we look at how this works, in a non-Hazelcast way, it's like you have a client, the protobuf compiler built us these stubs. We call out through a managed channel, and then there's a service implementation that runs on the server side. So that's what we're starting with. I had this initial vision that I would just build sources and sinks that knew how to talk directly to the managed channel. So that when it does a read from, it's just pulling something right from the managed channel, passing that on to the pipeline. So this is like a really clear diagram, but it kind of violates the way that gRPC works and the way that Hazelcast works. First of all, the managed channel, the code that you write doesn't talk to the managed channel. The generated code that gRPC builds for you handles all of that. And then you're just supposed to implement the APIs. So we're immediately, if I did it this way, building something really fragile that's going to break as soon as gRPC does any sort of revision. The other thing is that managed channel is shared by a lot of different APIs. So in our simple case, we had we had the hello and the chat and the, add things. All of those messages are coming through the same managed channel. So we would have to have a single pipeline handle them all. That's not good design from a jet point of view. That, a pipeline should kind of do one thing. It should be specialized to handle one message. If we made a single pipeline, I mean, we could do it. We could make the first stage in our pipeline, other than the read from, a filter and filter out, well, these messages go this way, these messages go this way. But now any change to anything requires me to redeploy the entire thing. So I'm really, from an operations point of view, not a smart way to do it. So what I ended up with instead is that we're going to have this service implementation layer that takes the messages and kind of parcels them out, saying, okay, if you're this message, go here. So we're really just taking that single managed channel, and in this case, forking it out 4 different ways, saying, depending on which pipeline you're talking to, I will write you out to a different queue. And then the gRPC source and sink are essentially going to write to those queues. And then finally, the jet pipelines will, as always, read from the source, right back to the sink. The piece in the middle, this buffer pair, is actually where all of the complexity came in. The service implementation is really very straightforward. The pipeline implementation, well, it depends on what you're doing, but since I had simple APIs, the pipelines are simple, the source and sink are simple. The complexity kind of came here in this buffer pair, that I need to make sure that the requests that come in get paired up properly with the responses going back. And essentially, and we'll see this over the next couple of slides, but just, to give a spoiler, we essentially do that by tagging everything that comes in with the UUID. So we create a unique identifier for everything so that we can trace it through. It's like, okay, we write it out to the source when, the pipeline is going to have to keep track of that and make sure to pass it back to us. And that's how we're going to respond back, or write it back to the proper response. So that's essentially what we're going over here. The sources and sink need to be used as a pair. We'll read from the source, write back to the sink, and then the buffer pair is how we are going to associate those together. So how does this look from the caller side? This is now the implementation of, it's on the server side, but it's where I'm extending that generated code. So for my hello, this is exactly the same signature as we saw in the non-Hazelcast version. I say I need a buffer pair that takes a simple request and responds with a simple response. I'm showing here creating it on the fly. In reality, I'm just doing this so it fits on the slide. I'm creating these in the constructor of my class and then just looking them up. So I'm not creating a new one on every API invocation. I create a new unique identifier, and then I call my buffer pair handler essentially, saying, here's my request, the identifier I just created for it, and the request itself. And then I, using that same buffer pair handler, say, now give me back the response. In this case, this is going to block because there's nothing else I can do for it. And then once I get the response back, I will pass that to the gRPC response observer saying, here's your response. And because it was a unary response, it's completed. So it does not look very much different than the non-Hazelcast version. We're just calling this buffer pair response. Now, if I jump ahead to what's the actual pipeline look like, it uses the gRPC connector, which is not the standard Hazelcast connector, but this is the one that I wrote for this project. And that connector has both a unary source as well as a streaming source, and then a unary sink as well as a streaming sink. So when I initialize this, I say, well, here's my project name and my API name, just so I can segregate out traffic for different APIs. And then I just want to map my request to a response. So the request is what came in from the connector. I get that unique identifier off of it because I'm going to need to preserve that. I get the name that was passed in as part of the request, and then I build my response. So I use the gRPC provided builder to build my response. This part is absolutely the same as what we did in the non-Hazelcast version. What's new is this is a type that I created for the library. It's like, okay, I want to wrap that response around so that it carries the identifier with it, and that's what I return. And then in the next or final pipeline stage, I write out to my unary sink, again, giving it the same identifying information so it knows where to route that. So again, the pipeline, really simple, just read from the connector, make your response right back to the connector. This is the same thing, just showing a streaming source rather than an individual unary source. This is the add API where we're going to get, again, a streaming response in, but only have a single response to go back. So streaming requests. We map this out. I actually make it into a three-part here because I've got the identifier, I've got the message, but because it's streaming, I also want to track. It's like, have we received the indication yet that the stream is complete? And so I'm going to use a rolling aggregate to sum each one of these as it comes out. And if we just passed every one of these through to the next pipeline stage, they would all get written back to the client. And that's not what we want. The idea is we don't write back to the client until we've got your answer. So we're filtering out all the ones where I'm essentially, this whole thing is pulling out this is complete. We'll filter out any that aren't complete and just throw them away. So we'll just get numbers and aggregate them, get numbers and aggregate them, get numbers and aggregate them. At some point when we see, oh, it's true, that was the last one, then it's like, okay, well, now we're going to build your response. So we build the response, set the output value, which is our accumulated value, wrap that into our with our identifier. And again, even though we read from a streaming source, we're writing to a unary sink. So we can mix and match these freely depending on the API type. And we write our response back, and then that gets routed back to the server. So that is as much, I mean, if there's specific questions and we want to go into any of the actual, code
Yeah,
for different pieces, we can do that. But I think we're probably a little bit constrained on time, so I'm
yeah.
going to,
So this is really good here, Mike. So we got a couple of questions, if you don't mind. So,
yeah.
can you address the security aspects when it comes to gRPC? How does it work in terms if you want to define security with gRPC and Hazelcast?
So, I don't remember the APIs off the top of my head because I did not put anything in it on the demo I was building. But I do believe there's various APIs on that managed channel that you can make sure that's encrypted. And I think there's the ability to do some, authentication of, whether you're an authorized user sending things through or not, but none of that is shown in the demo that I built. So that's all going to be kind of the built-in gRPC functionality. So I'll probably punt on that one and say,
Okay.
grpc.io is where, all the built-in features of gRPC are described.
So I will take this and just carry on answering this one. So Mike covered the service factory to create the gRP services. So what you can do essentially, you can use the service factory and manage channel builder to define your security, for example, service. So you could use, for example, if you want to plan to use TLS, for example, you can use transport security on the managed channel builder. So this will give you idea, but it's well documented in the API. My colleague has just shared this link in the chat box. So make sure to check the gRPC documentation. So are there any specific use cases where gRPC works better than other connectors and APIs we have?
My real reason for picking it is because I thought there might be, there might be a demand for it. I wasn't necessarily trying to say this is a better way to do it. And certainly if you look at the universe of things that are out there, for whatever reason, I don't know if it's because it was there first or because there's some superiority. But as I said up front, it's like, Spring seems to be the way that people are doing this on Hazelcast more than anything else. But I kind of but Spring again is kind of a Java specific way of doing this. I liked the fact that this gives us a lot of ability to tie into things that are written in other languages. So I think that was part of my appeal. I wanted to make a more polyglot demo. I actually didn't because I'm basically a Java guy. So I did everything in Java initially with the intent of going back and rewriting some of it. Once I had it, like, once I understood what I was doing, it's like, well, I can make different services in different languages and show how they all interoperate. I didn't get to that stage of it yet, but it's still on the vision board.
Yeah. So with that being said, thanks so much, Mark, for this useful content here. So anyone interested in trying out this demo, so we have the link on the GitHub. Feel free to try it out. And we are very excited to announce 5-point release for Hazelcast. So this is really a big move in towards the actual distributed compute for Hazelcast. So we have major release for advanced CP and CP map. You can try it out. We have the thread per core. Also, we have tiered storage. We added also the user code namespace, and we made a couple of connectors as GA. So it's very exciting. I would encourage anyone to try out the 5-point release. And if you are interested in any specific feature for 5.4 or any other features from Hazelcast, let us know. We can actually have a dedicated office hour in May for any features you requested. So with that being said, thanks so much for Mike for this nice presentation and demo. And I look forward to seeing you in May of office hours. Have a good day.